Hi and welcome. My name is Mr. Gaffey and you're very welcome back to Gaffey's Grinds. This is video 5 in our series on junior cycle electricity. So in these videos, we just previously looked at how to draw some electrical circuits, and we used a simulator to build some electric circuits. Now, of course, it's better if we were together and we could actually build some proper circuits, but it's not possible. So a simulation is a pretty good compromise. What we're going to do is we're just going to answer a quick few recap questions before we look at today's topic. So I have some quick practice questions for you guys to do here. As you see the questions here, they are question 1 to 4. So what I want you to do is I want you to pause the video and I want you to answer those questions from memory for me, please. And like I always say, if you're not going to do the questions, you're really wasting your time watching the videos. So pause the video and try your best at these questions now. Okay, so you should only be listening to my voice if you have tried these, and the answers are coming up now. So again, make sure you have them done. You're going to get a correcting pen, so a different color pen, red, green, purple, I don't care. And you're going to make sure you make corrections. So you either tick them or fix them. Okay, so either tick or fix. So questions 1 to 3 are done here. Okay, so what is an energy transfer? It's when energy moves from one object to another. What happens, which particles flow in an electric circuit? That would be electrons. Electrons are the particles that flow. And what happens to the coulombs of electrons? And a coulomb, if we remember, was a really large number of electrons, 6 quintillion electrons, a hell of a big number, okay, and that's how we count electrons. And what happens to these coulombs of electrons, these massive numbers of electrons, as they flow through a device? So as they move through a device, the device slows them down because the wire in a device gets really thin and this slows down the movement. And the electrons, when they slow, well, their energy that they had before they entered the device, which was much more energy, they were moving quicker, has to go somewhere, so it gets transferred to the surroundings. So what happens to the coulombs of electrons? They slow down and they transfer energy to the surroundings. Number 4 said to draw a circuit, draw the symbol for each of the following. A filament bulb, a motor, and a resistor. So really quickly, this is what you should have. A filament bulb has a wire, a circle, a wire continues, and inside the circle we put an X. This is a filament lamp or a filament bulb. Like that. Good. So either bulb, either tick it or fix it. So in my red pen here, this is what you should have. If you have that, then that is correct, as were these. So I want you to physically correct them. In the next one, ask for a motor. So a motor is a wire like this, a circle like this, wire continues, and we've got a capital M. This is a motor. Well done. If you got that right, again, tick it or fix it. If you don't have it right, get it right now, fix it. Okay, and a resistor. A resistor has a wire. It then has like a long rectangle like this, and then wire continues. This is a resistor. So either tick it or fix it. Okay, that's what you should have. Good. Now we're going to look at today's topic, which is where we're going to be looking at these devices, things like this, motors, bulbs, and resistors. And we are going to be considering the energy transferred by electrical devices. So devices like those, we're going to be considering energy transfer. Now, like we just discussed and revised in those questions, and we learned in previous topics, when electrons pass through an electrical device, they slow down due to the resistance of the device. So to draw this out, we would have, first of all, we have our wire, and in our wire, we have our coulombs of electrons that are moving. Why are they moving? Well, a potential difference has given the electrons energy, has supplied the electrons with energy, and this energy is what makes them move. So they have energy and it's causing them to move. So the voltage, which is the potential difference, comes from the power supply, like the battery or the main supply, pushes the electrons around the circuit, gives them enough energy to move. They then encounter a device. Devices are things like lamps, motors, fuses. Sorry, lamps, motors, resistors, things like that. And when they enter the device, so this is a device, like this, the coulombs of electrons slow down. So the electrons slow down. So that's what devices are. They provide a resistance to the circuit. So because the electrons are slowing down, we call this a resistance. So the device supplies the resistance in the circuit. Now the electrons will keep moving, because if they can't keep moving, then they won't flow at all. So they will only, electrons will only flow in a socket if it's a complete loop. So they have to be able to pass through the device and keep going. Okay, but they do get slowed down in the device. This is called a resistance. And when they get slowed down, well, they don't have as much energy anymore. So what happens is energy gets transferred out into the surroundings. Now, what is the surroundings? Well, the surroundings is everything that's not the socket. So everything outside the socket. That might be the room. It might be water if you're talking about a water heater. It might be whatever the surroundings of the actual electric circuit are. So quickly one more time, if we were to actually zoom in and have a look at what's happening. We've seen this diagram before. We have our wire, which is, I'm going to exaggerate the thickness and let these E's represent, each of these E's represents a coulomb of electrons, not just a single electron, a coulomb of electrons, which is a large number. There's a lot of electrons moving in here. It's not just a couple. Then they encounter a device like this. And the device basically has a way of narrowing the socket to provide what we call a resistance. Now remember, the coulombs of electrons are moving at a certain speed, and we call this the current. So how quickly are the coulombs moving in the socket? We call this the current. And the current depends on the potential difference. The more energy that's supplied by the potential difference, the more amount of volts that's supplied by the power supply, the quicker the electrons are going to move. So first of all, the current depends on the potential difference. Higher potential difference gives us a higher current. We've seen that previously. And then the electrons encounter a resistance in an electrical device, and this slows them down. So now the current also depends on the resistance. If there's a big resistance, the current is going to decrease. If there's only a small resistance, the current will decrease by a little bit, but not a massive amount. Okay, so the current is dependent on both the potential difference. Higher potential difference means higher amount of energy, and the electrons move faster. But the current also depends on the resistance in the socket, which is working to slow the electrons down. And of course, we know that what happens here is when the resistance is applied in the socket, some of the energy these electrons are carrying they do not have this energy anymore, because if they did, they'd still be moving at the same speed, but they're not. They get slowed down, which means energy is getting transferred out into the surroundings. So a device transfers energy from inside the socket to outside the socket. And at the very first video we did, we discussed that was the whole point of electric circuits, that they are a way of transferring energy from inside the socket to outside the socket, and that's why they're useful. Now we're going to consider just three of the devices and how they transfer energy. We previously learned in our previous topic, when we did energy, we learned about different energy transfers. So we're going to be revising that today. And this is we're seeing how this links up, how science topics tend to link up a lot. Is they're not just one little package and that's it. We never learn about them again. Science is all interrelated. And we're going to see that here now. The first thing we're going to consider is we're going to consider the device that is this guy, the light bulb. Okay, so the light bulb. Now, if we were to draw the light bulb, the scheme of the light bulb, like this, like we just did, we've got our coulombs of electrons moving. And again, how quickly are they moving? That would be the current. The current depends on the potential difference. So the voltage is going to tell us how quickly these electrons are being pushed. They're then going to encounter a resistance inside the bulb. So inside the filament lamp, we're going to supply a resistance. Down. Come on, stop messing around. There we go. Resistance. So the filament lamp is going to supply a resistance. I don't know if you've ever looked closely at one of these old style filament lamps, but I'm hoping here that you can see this section here. Okay, this bit is called the filament. Now, obviously the electricity comes in one of these wires and leaves in the other wire. So it stays a complete loop. So the electricity comes in and it stays a complete loop and goes back out. It has to. So the electricity comes in and goes out. So this loop here, this is our resistance. This is our device. Resistance. But where the resistance really applies is this circle here. So the reason for this is a wire made of tungsten. Okay, tungsten is a metal that's got a really high melting point, which means it can get really hot without melting. And it's all like looped up. Okay, so I can't zoom in enough to show you, but this wire is really thin and it's really looped up. And what this does is when the electric current reaches this resistance of this piece of wire, it gets slowed down a lot. And what happens is when it gets slowed down, this wire gets very hot because literally the electrons are being forced through this thin wire, and that's going to make it get really hot. And it gets so hot that it starts to glow, and it starts to transfer heat out to the surroundings as light. And light, this type of transfer, we call this a wave transfer. So you will remember that from our previous topic when we did energy transfers. So the bulb here provides a resistance with this very thin piece of tungsten wire, and it transfers. So as the electrons get forced through, or the coulombs of electrons get forced through, they slow down and they transfer energy to the surroundings. So the resistance slows down the current and energy is transferred to the surroundings by wave transfer. And the wave transfer is in the form of light. So light is a type of wave. So wave transfer, the energy is transferred to the surroundings as light, and that's why bulbs are useful. Okay, so that's how a filament lamp works. Of course, we know that this guy, if we were to draw this as a symbol, looks like this, a circle with an X. That's how we draw this. Same thing, okay? So essentially, this zone here is that circle and an X. Now, I don't want to do that because it's messy, okay? But just so you know, where that zone, where the wire narrows there is actually your device, which is your filament bulb. The next thing we're going to look at is the motor. Now, the motor is very similar. It's got the same scheme. You've got your coulombs of electrons traveling in the wire, and how fast they are traveling, that is the current. And the current depends on how much energy the coulombs of electrons have. And of course, that depends on voltage, or the potential difference. And when they get forced through this little section here, which is your device, this is a resistance. So the device here is causing a resistance. And the resistance this time is your motor. It's inside your motor. And this here is a simple motor, very small, simple motor. And what happens is energy is transferred, in this case, by mechanical working. Mechanical working. And what happens then is the motor is able to spin and is able to make things move. So you can attach something to this little to this part of the motor here. This will spin around and you can make objects move. So this object you could put like a propeller on here, and this object could then push another, like you could put a gear on here. This object could push another gear, and you could start to you get mechanical work, and the energy gets transferred to the next gear and the next gear and the next gear. Okay, so that is mechanical working. Energy is transferred out of the circuit by mechanical working. Now the electrons keep going, and obviously they will be going slower at this point because they have lost some energy. So before the device and after the device, there will be a difference in their speed because energy has been transferred. I just want to show you this here. This is two giant motors, one here and one here. Okay, so it's just like this. That's a really simple, small motor. This is a very large motor. I don't know if you can see what it's attached to, but that's a wheel assembly. So you've got some brake discs here. You've got basically a wheel hub here that your wheel is going to attach to. So this is the back end of a Tesla, okay, a Tesla car, which is they're a very simple car, really. They just have 4 giant motors, one for each wheel. That's basically all they are. They don't have an engine. They have a battery pack, and they've got giant motors. One goes to each wheel, and that gives you loads and loads and loads of mechanical working, make your car move. Okay, so very efficient and future is the technology of the future. Next one here we're going to look at is a resistor. Okay, so how does a resistor transfer heat? Well, same scheme again. You have your coulombs of electrons moving in the wire. They encounter your device, which is a resistor, and they have to squeeze through the resistor, if you like. And as they do so, they slow down, and energy is transferred to the surroundings. So the resistance reduces the current, and energy gets transferred by heating transfer. So energy gets transferred as heat in a resistor. So this is a simple resistor that we will put into some very low, simple powered circuits. And you can buy, these are fixed resistors. You can buy different resistors that are fixed for different resistances. But other things that use resistance wires that cause a high amount of resistance and will transfer by heating, is an example is a toaster. So here you have a toaster, and in here, I don't know if you can see the red hot wires. Well, each of those is a resistance wire, and resistance wire is designed to be able to get very, very hot. Now, resistance wires, basically this tells us another thing, and that is that the link between, if we take a look at the coulombs of electrons, resistance wire is obviously going to transfer quite a lot of energy to the surroundings, because heating, it requires a hell of a lot of energy. And we increase the resistance by increasing the length of the resistor. So in this case, we're making the resistant wire much longer. And what this does is it increases the resistance and it slows the electrons down more. And when this happens, I'm going to show, using more than one arrow now, a lot more energy is being transferred by heating. So these type of resistors, you usually don't want them to get very hot. You're just trying to slow down the current in a circuit for another device usually, because you don't want too much current going into certain devices. So you use a resistor before, for example, an LED. So an LED, you don't want very much current going into them or you'll blow them. So you usually put a resistor before an LED, and that slows down the current so it doesn't burn out the LED. But sometimes you want stuff to get hot. So you would use a much longer resistance wire, which has a high melting point. So it's able to get hot without melting, and it's able to get really hot and transfer energy by heating. Another example that you might find this in is something like a kettle. Kettles have basically a heating element in here, or a hot water tank would have a heating element. And what this would do is it usually looks like you've got if you look into the kettle, sometimes you'll see the element has like a steel casing around it. And, you know, you might have like, trying to think of the best way to draw this now. You know, you might have like a loop of, I can't draw it, but you'll have a steel casing, and inside you'll have loads of wire that's all curled and coiled up. So to make, by curling all the resistance wire up, you can make it really, really long and make the resistance much higher, and that will allow for much more heat to be transferred. Sorry, I can't do a good job of drawing that now. So, but just know that the longer the wire, the more resistant they're going to be, and therefore the hotter the more heat is going to be able to be transferred. All right, it's time to do some practice questions now. So the first thing I want you to do is I want you to complete these sentences, please. So I'm going to show you how to do the first one here. So you're going to say, when electrons enter a device, they something. So I'm going to model this one for you. Well, what do? They slow down, and I don't know, slow down is fine, because in the next sentence, we're going to talk about what the result of that is. So they slow down. When electrons enter a device, they slow down. Okay, so what you have to do now is you have to finish the rest of those sentences off in the same way. Now, do write out the whole sentence. Don't just write down at the end, because you're practicing writing and putting ideas together, and that's important. That's the whole point of this. So I want you to pause the video, write out the whole sentences, but finish them off with something that you think makes sense. Okay, so pause the video and do that now. All right, this is what you should have. Okay, so when electrons enter a device, energy is transferred to the surroundings. When electrons enter a lamp, energy is transferred by wave transfer as light. When electrons enter a motor, energy is transferred to the surroundings by mechanical working. When electrons enter a resistor, energy is transferred to the surroundings by heating. The last two are the hardest ones, but hopefully you managed to get it. When there is a high resistance, what happens to the current? The current is reduced. When there is a high potential difference, the current is increased. So if you think about that, put a stronger resistor, then you're going to slow the current down more. You're going to slow the electrons down more, so you're going to reduce the current. In our previous video, when we looked at our simulator, we saw that if you put more and more batteries into a circuit, the electrons move faster and faster and faster. So putting more batteries in is supplying more potential difference. So the last one, when there's more potential difference, or when there is more batteries, or when you turn the power up, you're going to make the electrons whiz around faster. So the current gets increased. That's really important. Those two are really important relationships for the video, for our next couple of videos coming up. That relationship between current, resistance, and potential difference. So really make sure that you have got those correct now. Right, a couple more questions, putting all of our skills together. Okay, so the first thing I want you to do is I want you to do question 1 first of all. So pause the video and draw them 4 circuits for me, please. Okay, so you should only be watching the video if you've done question 1. These are what you should have. Okay, so here is A, B, C, and D. Okay, as you can see, A is a device with a 2 batteries, or 2 cells, a resistor, and a lamp. That's what we were asked for. B is here. B is here. It's got 3 cells. It's got a resistor, and it's got a closed switch. That's what we were asked for. C, we have 2 cells and we have a motor. Is that all we were asked with? 2 cells and a motor, yeah. And number D is here. We have 2 cells, we have a closed switch, we have a motor and a lamp. Now, how did I know that I needed that? Because that's not exactly what I was told. Well, I was told you need 2 cells and a motor, which can be turned on and off. So that tells me I need 2 cells and a motor, and I need to be able to turn it on and off. Well, how can I turn on and off a motor? Well, I put in a switch. Switches let me turn on or off. So that's where I got that from. So that's why we should have a switch in there. When the motor is on, a light also comes on. So when the switch is closed and the motor is on, then I need a lamp to come on as well. And that's why I've got the lamp over here. So you should have a motor, a lamp, a switch, and 2 cells. Okay, good. Right, now I want you to pause the video and I want you to do numbers 2, 3, and 4. Really have a think about number 4 as well, because there's 4 options. You have to try and choose the right one. All right, so pause the video and do that now, please. Okay, so question 2, toasters transfer energy by heating. Which electrical device are they most like? Well, out of the ones we've studied today, they are most like a resistor, because resistors transfer by heating. So toasters contain resistors. Okay, so they are like resistors that they transfer by heating. Well done, if you said that. What are the units for potential difference in current? Potential difference is volts, and current is measured in amps. So you should have potential difference is measured in volts, current is measured in amps. Well done, if you got that right. And which of the following will have the highest current? Okay, let's consider these options. A circuit with high potential difference. Okay, so high potential difference is going to make the electrons fast. And high resistance. Well, high resistance slows the electrons down. So they're going fast in the beginning, but then they're going to be slowed down a lot. So, well, let's see the other options. What about B? A circuit with a high potential difference. So, yeah, electrons moving quick. That sounds good. But a low resistance. Yeah, well, low resistance isn't going to slow down the electrons very much. So the current there will be high, very high, because we've got electrons being pushed with a lot of energy. So they're going to move fast, so current's high. and resistance is low, that means it's not going to slow down the current too much. So yeah, that sounds good. I'm going to just put a little tick beside there, but I'm going to read the other ones just in case. A circuit with a low potential difference, they weren't going very fast to begin with, and a high resistance. Oh, that's going to slow them down even more. Definitely not that one. I'm going to rule that one out for sure. A circuit with a low potential difference and a low resistance. Okay, well, that's better than the one above it. Low potential difference, so not much energy to start with, but not slowing them down. Okay, yeah, but still definitely not going to be as high a current as B. So the answer is going to be B. A circuit with high potential difference and low resistance will have the highest current out of those four. Okay, so I'm just going to show you the written answers. So if you need to, you're going to pause the video and make any corrections right now, please. All right, that's the end of today's video. Okay, in our next lesson, we are going to look closer at how we measure current and voltage in a circuit. Okay, we're going to be looking at how we measure current and voltage in a circuit, and we're going to be looking at the relationship between the three things that we can measure: resistance, voltage, and potential difference. We're going to look at how they affect each other. We've already kind of looked at it today. We've already learned that this here, F and G, when there is high resistance, the current is reduced. So high resistance, the longer the wire of the resistor, the slower the electrons, the more the electrons get slowed down. So the current, I, current will reduce. When there is a high potential difference, so that means a lot of energy has been transferred to the electrons in the battery, they're going to move faster. So the current is increased when the potential difference is increased. Okay, so we've already laid the foundations for the future videos, and I'm going to see you in the next video. Thanks for watching. If you found this useful and it helps you to understand how energy transfers happen, please do give us a like, because it helps other people to find the video that may also benefit from watching it. And if you found it simpler to understand than in a book, or when you did it in school, please do leave a comment saying why you found the video useful, because that also helps the videos get found. If you need me to do anything else, if you'd like me to do a video on any other topics, do leave a comment about that as well, and I'll get cracking on it. Thanks, guys. See you in the next one.